Every electronic device requires a power supply. The power can be provided by a battery or via the power grid. Since electronic circuits often need different voltage levels, and sometimes quite a lot of them, a power supply unit is required. Various circuit topologies are used for this purpose. The most important types are linear voltage regulators and switched mode power supplies. Nowadays, linear regulated power supplies for power applications have largely been replaced by switched mode power supplies. However, there are still some applications where they play an important role, such as generating reference voltages or low noise power supplies. And that is why it is worth taking a closer look at them. Before we start with the regulator itself, let's have a quick look at the typical design of a linear power supply. If we are dealing with AC voltages from a power grid, typically there is a transformer at the beginning, which converts the mains voltage into a lower AC voltage. The transformer also provides galvanic isolation, which can be very useful in some applications. Since the output of a transformer is always an AC voltage, it must be converted into a DC voltage by the following rectifier and filter capacitor. This can be done by a half-wave rectifier or a bridge rectifier. Unfortunately, as the load increases, the voltage breaks down more and more. So what we have on the output is a DC voltage with an AC ripple voltage overlaid. This pulsating voltage has to be stabilized by a following regulator, which can be done by either a linear regulator or a switched mode power supply. Before we turn to the linear regulators, let us take a closer look at the design of the transformer and the filter capacitor. A transformer converts the input AC voltage into a higher or lower output AC voltage. The following rectifier converts the AC voltage into a DC voltage. This DC voltage is square root of 2 times lower than the peak voltage of the input, minus the losses at the rectifier. They are typically 0.7 volt for a half-wave rectifier and 1.4 volt for a bridge rectifier. If we need a certain minimum voltage on the input of our regulator, we have to consider the whole chain from the AC input to the output of our rectifier. For example, we want to have a minimum voltage of 9 volt with a maximum current of 1 amp. We know that the voltage at the capacitor is pulsating. We choose a maximum voltage drop of 3 volt at the capacitor. With that voltage drop and the maximum current, we can calculate the value for our capacitor. The variable T is the time difference between 2 load cycles of the capacitor. It depends on the type of rectifier we are using and of the frequency of our AC voltage. Although we allow a voltage drop of 3 volt, the buffer capacitor is really big. This is typically for power supplies with a 50 Hz transformer, and is one of the reasons why primary switched power supplies are much more common today. We will discuss this type of converter in one of our next videos. Now let's get back to our example. The voltage on the output of the rectifier with no load has to be minimum 12 volt. In addition to that voltage, we have to account for the losses of the diodes in the rectifier. Suppose we have a bridge rectifier where we have to consider 2 diode voltage drops of 0.7 volt for the positive and the negative half wave of the AC signal. That means we have a minimum input peak voltage of 13.4 volt or 9.4 volt RMS. The main voltage in most of Europe is 230 volt RMS. The tolerance of this voltage is plus minus 10%. That means we need to raise the minimum voltage by 10% just to be safe. For our example, we now need about 10.4 volt RMS on the secondary side of the transformer. Or in other words, the transformer needs a voltage ratio of about 22:1. This example shows how you can choose the right transformer and rectifier to get the non-regulated DC voltage. But if we want to obtain a clean, ripple-free and constant voltage regardless of the load, we need a subsequent regulator. we can build ourselves a linear voltage regulator for this task. So let's get to know a few circuits and topologies to achieve our goal. There are two main types of linear regulators, the series and the shunt regulator. The main difference between these two types is whether the regulator is connected in series or parallel with the load. Regardless of our choice of regulator, a few parameters are important. They can be used to measure the quality of different regulators. Those parameters are output voltage, maximum output current, dropout voltage, which is the voltage that must be supplied to the regulator above its rated output voltage, line regulation, which is the ability to maintain a constant output voltage despite changes to the input voltage, and output resistance. If we want to use a linear voltage regulator for power applications, the series regulator is still widely used. As mentioned above, the regulator is in series with the load. The main element is often an NPN transistor, which is connected as emitter-follower. A constant reference voltage is applied to its base, which, for example, is generated by a Zener diode. It is easy to see that the voltage on the output of the transistor is the same as the Zener voltage minus the base emitter voltage. Since power transistors often have a very low current gain, the simple NPN transistor is replaced by a so-called Darlington transistor. This is a special type of transistor circuit consisting of two NPN transistors in which the total current gain is calculated by multiplying the individual gains. The use of a Zener diode as reference voltage works quite well, but has some disadvantages, in particular for line regulation. Therefore, most voltage regulators are built with a control amplifier. The reference voltage for the amplifier can again be generated by a Zener diode. But in most common integrated regulators, this is usually done by a bandgate reference, which is much more accurate. This is the typical design used in millions of integrated voltage regulators, but it has a serious disadvantage. The dropout voltage, which is the minimum needed difference between input and output voltage, is very high. To find the reason for that, we take a closer look at the principal circuit of the integrated voltage regulator from the widely used 7800 series. Let's start with the Darlington Transistor T1. Its major advantage is that the small base current is enough to switch a large collector current. But since it actually consists of two transistors, we need a base emitter voltage of about 1.4 volt instead of only 0.7 volt. Next, we want to consider the resistor R3. It is used as a simple method to limit the output current. If the voltage drop over the resistor exceeds approximately 0.7 volt, the transistor T2 starts to conduct and the Darlington Transistor T1 starts to limit its current. Finally, the current source I1 needs at least 0.3 volt to work properly, because of the transistors inside of it needs to be in saturation all the time. If we sum up the base emitter voltage of the Darlington transistor, the voltage drop over the current limiting resistor and over the current source, we get the minimum voltage drop over the regulator. Is the voltage drop lower than that? We cannot tell how the regulator behaves. In a worst-case scenario, the regulator could give a higher output voltage than normal, which could be critical for the subsequent electronic circuit. The large voltage drop is one of the reasons why the efficiency of such regulators is very poor, often even below 50%. Sometimes it is not even possible to have a high enough input voltage for a correct operation of the regulator. But fortunately, the development has not ended here. To get around the problem of large dropout voltage, a new controller was invented by National Semiconductors as early as 1977. Up to this day, the company claims the title for itself, inventor of the low dropout voltage regulator, or LDO. We will take a closer look at LDOs and other things in our next video. For the interested viewer, we highly recommend The Arts of Electronics by Horowitz and Hill, and for our German-speaking viewers, Elektronische Schaltungstechnik, written by members of our institute.